In this video, we'll be solving quadratic equations, and the strategy that we'll be using is taking the square root. And we're going to start off by looking at some squares that were made on virtual geoboards. And on this first virtual geoboard, we are asked to find the area of the square. So we have to count the side length. And what we do when we count side lengths is the distance from one peg to the other is 1, 2, 3, 4, 5, 6. So this particular square is side length 6, and just to make sure it's a square, let's count this side. 1, 2, 3, 4, 5, 6. And so to find the area of this square, how many little squares make up the square? I could certainly count them all, but that would be a lot of work, right? We know how to find the area of a square. We multiply the side by itself, so the area of this square is actually 6 to the second power. The area of the square is 36 square units. And so the relationship that we remember between the side length of a square and the area is if I know the side length, I square it to find the area. So we can apply that same principle to this smaller square here. The side length of this smaller square is 3, and therefore the area of this square would be 9 square units because it's 3 to the second power. Finally, over here, I'm told that the side length of a square is 8.5 units. So therefore, the area of this square would be 8.5 units squared. And so that would be 72 72.25 square units, which is 8.5 quantity squared. So the relationship between a square and its area actually plays a part in what we'll be doing today with solving quadratic equations. So let's look at the next example. In this example, we are given the area of a square, and the area of the square, we're told, is 25 square units, and we're asked to find the side length. So remember, the relationship was the side length squared equals 25. So I would ask you the question, even though I can't count pegs here because it's on a diagonal, what must the side length of this square be, which when I multiply it by itself equals 25? So the side length of this square must be 5. Okay, over here, they did not give me the area of the square, but I can figure it out. If I draw this line going down, I actually have 2 congruent triangles, and the base of the triangle is 4, and the height is 2. And we know the area of a triangle is half of the base times the height. So half of 4 times 2, that's half of 8. And half of 8 is 4. So this piece is 4. This piece is also 4. Therefore, what's the area of the whole square? The area of the whole square is going to be 8 square units. So if the area of the square is 8 square units, what must one side of the square be? Well, it's not going to be a rational number, is it? Because there's no rational number which when I multiply it by itself equals 8. So here we have an example of a square with an irrational side length. And some people might like to simplify that irrational number, which is fine. But for the purposes of our talk right now, if we know the area of a square, The side length is just the square root of the area. So keeping that in mind, we're given the area of a square is 39 square inches. Therefore, the side length is going to be the square root of 39 square inches. And therefore, the side length is the square root of 39 inches. Okay, so we're going to be squaring numbers and taking square roots as we solve problems in this particular problem set. So let's look at our first two problems right now. We're looking for the value of n, some number, which when I square that number equals 121. So somebody might say, I can do that in my head. I know that 11 squared is 121. And I might say, yeah, but there's another number which when squared also equals 121. And that would be negative 11. And so what I want you to think about is when we isolate the variable and we undo taking the square of a number is square root, and I take the square root of both sides of an equation, it's really important that when we're solving an equation and my strategy is taking the square root of both sides, that you end up with two solutions, a plus and a minus. And the square root of 121 is 11. And so it turns out when we solve quadratic equations, very often we'll have two solutions. Sometimes we'll have one solution, and other times there will be no real solutions. But right now, let's think of the case where there'll be two solutions, okay? So we're going to move over to this problem here. And we're saying 3 times some number squared is 300. And I always encourage students to think of a number using mental math, which when you square it and multiply it by 3 equals 300. And some people might come up with that solution, and that's great. But then we want to know, is there kind of a system that would work for us to isolate this variable every time? Oh, definitely. This variable is being multiplied by 3, so I'm going to divide by 3 to get the variable term all by itself. Now this variable is being squared. And so to undo square, the inverse operation of square is square root. And this is where we talked about a moment ago that when you're taking the square root of an equation, your answer is going to be plus or minus, and then the square root of 100 is 10. So those are my two solutions for that equation. So we'll do a couple more examples, and hopefully that'll get you thinking about how to solve quadratic equations by taking the square root. All right, so here's my last two examples. So the first thing that I would ask you over here is think about this quantity as like some number. Some number squared equals 81, right? And then you would say, well, what number squared is 81? Okay, 9 squared. So what would x have to be in order for x plus 4 to be 9? And you can think of one solution that way, but then you would also have to think, well, wait a minute, what if inside this you had negative 9? Negative 9 squared also equals 81. So what number, when you add 4 to it, equals negative 9? So you can solve these using mental math, and I never discourage people from using mental math. But you can also solve them directly, because in this case, my term involving x is isolated. It's all by itself. So I have to now undo squaring by taking the square root. And the square root of x plus 4 quantity squared is x plus 4. The square root of 81 in this case is plus or minus 9. So this means I have two, you can think of this as answers. We can say x plus 4 equals 9, right? That's one. Or x plus 4 equals negative 9. And so I'm going to subtract 4 from both sides. And earlier, you probably already thought of 5 as a solution. So good for you. But when I subtract 4 from both sides here, I don't get negative 5, do I? I actually get negative 13. And so a lot of times you'll see the solution to this quadratic equation written like this. Using these braces, this is a way of showing a solution set, and we typically put the smaller solution first and the larger solution second. And so you can always check, is this answer right? Well, let's plug it in. Negative 13 plus 4, what's that? That's negative 9. Negative 9 squared, what's that? That's 81. Yay. So I know this answer works. Now let's plug in this number. 5 plus 4, that's 9. 9 squared, that's 81. All right, so this example over here, I'm going to change my color. We don't have the variable term isolated yet. We have to isolate that variable term by first dividing by 5. And so when I do that, I will now have my variable term isolated. And let's think about this with mental math. If 250 divided by 5 is 50, then 245 divided by 5 must be 49. You could also use a calculator, of course. And so at this point, you're going to want to get rid of the square. So how do we undo square? We take the square root. So we're left with x minus 1 on the left. And on the right, you're left with plus or minus 7. And so the two equations we can write look like this. X minus 1 equals 7, or x minus 1 equals negative 7. What number minus 1 equals 7? Add 1 to both sides. 8, that's a possible solution. Add 1 to both sides. Negative 6 is your other solution. So we have two solutions for this one, negative 6 and 8. And so hopefully you feel like you could try some of these examples on your own, solving quadratic equations by taking the